We are recording now. Cool.
Hello, future people.
Uh, so today, we're not gonna check the book out. We're not gonna go to L3. Today's goal is to pick L2, which theoretically we have it. We have it done. It works. And we're gonna actually call the evaluator after the compilation process. That's the idea. So Mario, I think I asked you this before. So do we have to do any sort of management of program counter, or is this happening by itself?
I'm pretty sure the instructions as they are implemented already do that. Although I could be wrong. So.
You could be wrong. This returns a compiler and a store. My understanding is that we don't care about the final version of the compiler.
Yeah, no, we just care about the store, which contains the memory image of our compiled program.
Yeah. So my understanding is that we actually need to create a computer. So we need to do something like uh, a machine and then initialize. And I think you pass units to that. And we actually need to update this machine with this new store, right? I believe we gotta do that.
Yes.
Okay. Um, so in that particular case, I'm gonna do the pipes. So pick that, and I already forgot OCaml. So what's the syntax? This is the syntax. Hmm. Actually, that's a good question for Magetta. Magetta, what's the best way of doing this?
Let me see. Do what?
I want to pick whatever is coming out of the pipe and put it
Mm-hmm.
in here.
Oh, yes, that's a very good question. You cannot.
Damn. So I need to make a
I
lambda
mean,
just for that.
for you to update, you can use the same. If you put the variable with the same name as the field, then you don't need to assign, right?
Can't I also just do something like this? Does that work?
If it picks the right value and you are going to return purely, yes, you
Maybe.
need the parentheses.
Yes.
Yes,
There. Not there.
yes.
There. Okay. Definitely works. So initialize the computer, swap the store, and then what do we do? I believe, Marin, we need to make a. Ooh, very famous. We need to make an evolve function. Do you agree?
Yeah, I do.
Okay, so what a circle. All of this to come back to evolve. Uh, so we're gonna have a computer, which is machine T. And what's gonna be the output of this unit?
Uh, Maybe it should output another computer.
It should put. So basically, after we run the program, that's kind of the idea then.
Yeah, it returns the final state of the computer.
And I think we're gonna have to do some a little bit of destructuring as well. So I'm gonna pick this thing and put it in here. Okay. Let's see. Let's see. What's the first step? Pattern matching.
Uh, let's see. We take the computer. Uh, Actually, let me just double check something real quick. No, evaluator. Put structure, set structure.
I think we need to pick the first element out of the store and do a pattern matching on it. I think that's what we need to do.
Yeah. Actually, yeah, I'm just looking at the instruction implementations we have at the moment. Yeah, they actually don't increment the program counter.
Oh, so this would not be done by the many registers like p registers and stuff like that we have. This is not being done by these functions here.
Yeah, we actually need to do that. Um, Either modify the instructions or do it in the evaluator, one or the other.
I feel it would be better to do it in the evaluator because then we don't pollute the functions that have textbook implementation.
Uh, from a more like, I agree that this will keep the implementations closer to the book, but we will have to have special cases like for jumps and stuff and calls, I guess.
Well, but how many special cases do we have? Isn't it just going to the machine here and see which one of these will be special?
Uh, Call and proceed, definitely.
Mm-hmm.
Do we have a return instruction? I think return is proceed, right?
I don't recall.
Yeah, I think it's just those two actually.
Okay, so I think it's worth it to do in the eval. What do you say?
Okay, I think that's okay for now.
Okay, so what are we gonna do? What I said, pick the first memory cell out of the store.
Uh, yes, we should like.
Do we have an operation to do such a thing?
Well, we can get stuff from the heap, so Although this wouldn't be in the heap, this would be in the code, right? So
Yeah, no, we are
it would be a
definitely getting this thing,
yeah
this
code
section.
get.
Yeah, but we don't have the index. We're gonna have to create like a. This is gonna be a
We can
recursive
just
function.
we can just say the index is 0 to begin with. Like I think, um, do we have a program counter register? We do, right? It's except it's not called PC, it's called P, I think.
Yes, I think it's the P register, and we do have one of those.
Yeah, we can just set it to 0 to begin with, and then at every iteration of eval, we look at the P register to grab the next instruction.
Okay, but we need to do some. But I think that's already the case, Marinho. Let me see. Where is the initialize function for the computer? Yes, yeah. See, it's already 0.
Well, in that case, we can just look at the P register, grab the encode, grab the instruction at that address, and dispatch on it. Just do a pattern matching.
Okay, so match store dot code. Oh, I need to do the. I need to disable company before Magenta has a thing there. Okay, so code get. Um, I already forgot. Oops. We do code. Not that. Code get, and we pass the thingy and the that and which yeah okay. So we pick the store, which means that we also need the p register. P register. P register uh, with syntax error. Maybe I need to put parentheses in here. Okay, so now we pattern match on these things, right, Marinho?
Yeah.
Okay, so I'm just gonna copy those. Let's put the special cases at the bottom. Let's put the special cases at the bottom, at least for now. Uh, then we gonna do one by one, I guess. So the first one, get structure. This one, we're gonna have a tuple in there, in which we have another tuple. So here we're gonna have a register uh, with something going on here. And I believe we're gonna have a string and an integer here. I shouldn't have, yeah, removed that. So what is the name of the string again? Do you remember? Is it a name? Maybe. I don't remember what are the things on the
Yeah, it's
left.
the name of the functor.
And the arity of the functor there?
Yeah.
Arity. Okay. So I believe if you get a get structure, which it is complaining for some reason, so maybe it's because I need to do machine dot instruction dot. Is that how you do that, or am I doing it wrong?
Uh, wait, what are you
I
doing?
for I
Uh,
forgot. Oh, it's machine dot cell dot the thing. Okay, so that was wrong. So here it's cell. Should be replaced with the type expression. The constructor belongs to a variant of type lib machine cell dot instruction. So I do need instruction here. Is that? I don't remember. Do you remember, Marinho or Magetta?
hurry up, what?
We have this module called machine.
Said
Ins
hurry up, not remember.
yeah, no,
Sorry.
I got confused, but I said, okay, maybe Magetta is tired.
Yes, I am actually.
So we
Yeah,
have a
what's that?
module inside a module. So we have a machine, and inside that we have a cell. And
Mm-hmm.
inside that, I want to pattern match this guy.
Right, you just access cell dot get
Del
get structure.
oh, so it's
Not
just
this.
this one.
Yeah, without the
I
middle.
believe I'm gonna open this one.
That's probably good. Yes. You don't open like that inside of a function. It's
You
let.
need to do let open in.
Like this then.
Yep.
What is it complaining about though?
Probably
These
it's not
expressions should not
completed.
be unit literal. The expected type is leave.machine. Oh, it's because I'm returning unit here maybe. Let's return the computer here, just to make it happy. It's still complaining. This variant pattern
Mm,
is expected to have type cell.t. There is no constructor get structure within type machine lib.machine.cell.t. Do I need to do dot instruction here?
no,
No.
you can't open a type, right?
Yeah, that doesn't make sense. But is it is it what is complaining is that it's saying about this t, you see.
Oh, right. Yes, it's looking
But
at
we are
that
talking about
struct.
this one.
Wait, is it understanding that it's t instead of
Yes, it is. I can even show you why. You see this? Do you mean? Did you mean structure? Structure
yes?
is the one
Hmm.
available here,
Yes. Can you go back?
of course.
What does the get cold get return?
Code get. Oh, it returns an A, and in this case, it's an A. Oh, okay. So this is the problem. The store has a bunch of cell T's, Marin. It doesn't have a bunch of instructions.
Right. It needs to. We need to grab the cell, and then we need to check that the cell contains an instruction, and then we pattern match on the instruction.
Wait a moment. So you're
Yeah,
telling me that we
I
have? Oh, we do. So everything, every single other one is an unreachable. Okay. Uh, that's a little annoying, but okay. Because we're gonna have to immediately do a match here. And this should actually go fail with unreachable in eval. I made a convention in the compiler with these unreachables. Okay, so just the name of it. Okay, let's go. Okay, so now instead of doing that, I'm gonna do match instruction with, and now this is the thing, right?
yeah.
Okay. So my understanding is that we have a function called getStructure. Am I misunderstanding? Okay, this actually returns a new computer, in fact. Um, Okay. So let's see what I need to pass. I need to pass the functor label. So we have a name, we have an arity. Why do you need the register? Is that it? Oh no, you actually need to pass the register afterwards. It's just that they come as a tuple, these two. Okay, so you do this, uh, this, this, uh, p register equal p register. Uh,
You need to put the curly braces around the computer, no?
the curly braces you said.
Yeah, because
No,
you're saying get structure with the name and the arity, the register in the computer, and you wanna do the.
I want to get the output piece computer out of this instruction.
Oh, and then I see.
Yeah, but there's something wrong. Oh, I know why. It's because this is a register and this is expecting an integer. Damn. Okay, so we need to make a conversion.
Did we not update the functions
No, of
to make
course
a
not.
register? We didn't. Huh.
Yeah, especially because it was not clear at the time if the functions were going to use temporary registers or permanent registers.
They can use both. They should be able to use both.
Oh, so then we just need to extract the integer out of that. We already did this before.
No, but we also need to know which register we're operating in, right?
How does that change the behavior of the functions?
Because if it's a temporary register, we can just use the register directly. But if it's a permanent one, we actually need to reach into the stack.
Damn. Okay, I don't remember if. Okay, what do you mean by reaching into the stack?
Because permanent registers are just spots on the stack that were reserved to hold data between function calls,
Yes.
which means that accessing them is different from accessing a temporary register, which only exists in the computer state.
Also yes. But
Which means that depending on the type of the register, we need to grab the data from somewhere, some different place. You see?
okay. I guess it means that if it's temporary, we need to do that.
Yeah.
Okay. I don't remember. Does OCaml has this by any chance? Oh yeah. Okay. So can I just?
I think actually the better way to do this would be to just update the evaluator functions. Uh, although, although,
No, I think we should make a. I think you're right in a sense because we should make like a stack frame operation generically that you pass the register, it does the pattern matching there, and it receives the computer. And if it's an X register, it does the thingy, and if it's a Y register, it just keeps going.
the problem is that those instructions will need to interact with the register in different ways, and only the instruction knows what exactly it's going to do.
Wait a moment, but that means you're basically telling me that the behavior of all of the functions that interact with registers, they change depending if it's an X register or Y register?
Like the changes they do to the machine state is mostly the same. It's just that the data source or the data sink, if it's a writing operation, will change. You see?
But I thought that if it was a temporary register, we would just pop from the stack.
No, you mean if it's a permanent register, right? But it's not a pop. It's either a read or a write to a particular stack location.
I think I need an example. Which instruction do you think would be a great example for us to start?
Uh, Literally any of them. They all need to do these lemons.
No, but they all need to do this. But then I propose for us to make a generic function that we always gonna call before calling any of those. But then you counter argument that saying that the behavior from each one differs. So we need to go at each one of them necessarily instead of making a generic function.
Yeah, because like put structure is going to write to a register, get structure is going to read from a register. They do
Okay,
different things. You see?
okay, let's start with put structure. Okay, so what you're
Okay.
saying is that instead of being index of register here, we're gonna nuke that and do cell dot register here. Does that make sense to you?
Yeah.
Okay. So what is the first thing that you need to do to pattern match on the register, I guess?
Uh, let's see. I think not necessarily because this will only touch the register on line 12.
Yes. So before that we pattern match on the register then.
Yeah.
Okay. So if let's pick the register. Let's suppose that it is a temporary register. So index of register. What do we do then? That's what I'm confused. That I want to learn.
Well, if it's a temporary register, what we're doing is already enough. So we can just keep the current behavior.
Okay. Wait a moment. Okay. If it is a
In
Y
the
register,
Well, if it's a Y register, the X registers will stay the same, but actually change um, we need to change the contents of memory in this case.
do you mean the store?
Yeah.
Okay. Okay. In case of the X registers, we do the same thing.
Yeah.
Oh, so I was wrong then. This was already correct before. Oh, but I need the index of register. Damn. Okay, for now I'm gonna just copy paste. So pick this. It's exactly the same, right? There, there.
Actually, no. In the case of the Y register, we don't touch the X registers at all.
Okay, I think that's my first confusion. Why, if it's a permanent register, we don't touch the X register? Well, actually that already answers my question because these are the X registers, right?
Yeah.
We don't touch them if it's a permanent register. Makes sense. What do we do with the store though?
We need to reach into the stack, which is in the store.
Yes.
Specifically, we need to look at the topmost stack frame. There will be some registers, some Y registers stored in the stack frame. We just need to index into them and change the correct one.
Okay, let's go by steps because I think I understood some of what you said, but not all of it. Uh, the first thing that you said is that we need to pick something out of the store, right?
In this case, this is doing an add on the temporary register in line 14, right? So this was actually a write into the store, I think.
Yeah, so we're gonna write into the store.
Yes.
Okay. So I want to go back and go to the store. So we want to do a stack operation, you said, right?
Yes, we do.
So we're gonna write something into the stack frame.
Yeah, we're gonna do a stack put, although I don't remember. Stack put is in terms of the latest stack frame, or is it in terms of like the entire memory range?
Only stack. The operations that have prefixes, they're related only to themselves.
Well, yes, but does it take into account the entire stack or just the top frame? Because that matters.
I think the entire stack.
Okay. Okay, that's mildly annoying. We should probably make a helper for this then, because we're going to do like these kinds of operations a lot, and
Okay, so you want to
it would
make a
be a
helper here.
yeah.
So what would that helper be named?
Well, we need to get and put from the top of the stack, from the topmost stack frame, not the entire stack, because like that's a common operation.
Yeah, but
So
how
I
are we gonna
guess,
determine the size of the stack frame and stuff like that?
well, we have to look at the base of the stack frame, which is pointed to by one of the registers, although I don't remember which one. I think it's the S register.
I have absolutely no recollection, so S register. We do have a S register. I don't know if it
Uh,
does what we think it does, but it's being used a few times.
hmm.
This is
Yeah, I'm
a.
not.
I think this is a clue that this is not the stack stuff.
Yeah, no, it's probably a different register. I know there's a register that points to the base of the current stack frame. We basically need to use that register to.
Yeah, but I don't know if we have that register though. We have. Okay, we have all of these. Which one do you think it is? E?
I think it's. Yeah, it's either the E or the S register. One or the other.
Okay, which one do you want to bet? Wait, can't we read, do a grep on the book and see this type of stuff? There?
We could.
Do you have the book there?
Uh, Not really. Actually, I think. Let me scroll up a little bit. I think that picture I posted a while back of the paper will be more helpful actually.
You're gonna scroll up a lot.
That's why we have a mouse wheel.
Do you? I use an Apple mouse.
That's very sad, Mageta.
Yeah, that's very freaking sad.
Is it at least a three-button mouse?
It is. It actually has two buttons on the right and left. Right.
And it is a touchscreen mouse.
Actually, no. I'm joking because I actually do have a Mighty Mouse. You know the Apple. You know the old Apple mouse.
Yeah? Well, I don't know if
Yeah,
I
I have
know
that
actually.
one, which is slightly better. I mean, it's still not amazing, but pretty good.
Okay, found it. Yeah, I think it's actually. Yeah, I think it is actually the S register. Maybe,
Okay,
possibly.
maybe. Okay, so let's assume it is the S register. So what do you want to do? Oh,
uh,
we need to make an auxiliary operation, you said, right?
yeah, basically we need to grab the contents of the memory cell that's pointed to by the S register. That will tell us the size of the stack frame. We do a bounce check, um,
Then
and then we just index into the correct register from there. I think we need to skip like two or three positions because there's some meta information about the stack before we actually get to the Y registers.
I think that's on the chapter, the most recent chapter that we implemented before
It
L3.
is, yeah, it is. It is there actually.
Yeah, we should count if it's two or three there. But I don't think we need a helper for this. Do you think so?
Uh, I mean, it would be convenient, but I don't think we actually need it necessarily.
Let's do it like this. Let's do it first manually, and then when the pattern starts emerging, we make a thing for it. So this is gonna be store stack. We are writing, so this is a stack put.
Yes.
So what are we putting in there? What are we putting in there? I'm not entirely sure.
The structure, no?
We wait. What is the type of this? Oh, okay. So you're right. So you put the structure there, and we're gonna use S register on it, and this is gonna return us the new store. That's it. So now we need to jump a few spots, right?
We need to do that before we do the stack put, actually.
Uh, so let s register. Are we gonna change the are we gonna change the
Mm,
s register?
no, we're just reading it, not writing it.
Okay, so plus 2 then, or 3. Have to check that one out.
Yeah, it should be plus 2 plus the index, I think. Something like that.
Well, but let's actually open the book though, because as
Probably for the best. Yeah.
I think it's gonna be helpful for us to see that diagram that I 100% know it is in there because we look at that so much for so long. Can I click? I can't click to go. Cool. Why we have mouse wheels? Marinho 2025. Uh, okay, almost there. Here it is. Here it freaking is. Um, are we here?
Uh, well, this is allocate.
Oh, maybe it is this one, but this is talking about E register though, not S register.
E-registers, if I'm not mistaken, points to the next available spot on the stack.
Mm-hmm. Oh, that's different than the S register then.
Yeah, I think the S register points to the base of the current stack frame.
Okay, but in that case though, I thought it was this image. This is not
No,
the
no,
image, right?
but this is the right image. You see, um, because the E will become the next S after the allocate instruction is finished, if I'm not mistaken.
No, but the E doesn't. The new E doesn't use the S, Marinho. You see, the
Hmm.
new E uses only E.
Hmm. Allocate in sets a new E.
I don't have recollection of the S register because we just used it in the beginning. So I don't know.
I hmm. Maybe it is the E register. Let's see. Deallocate,
The deallocate grabs the E plus one from the stack.
which is the
Uh,
continuation point. Yeah.
and then
Okay,
calls
it
it.
actually is the E register then. All right.
Yeah, I was I didn't remember. I remember the E register, but not the S register. Okay, so now that we settle on this one, we do plus 2 and then you said plus the index of the register, right?
Uh, let's
Oh, because they are
see.
numbered from 1 to onwards. So we need to jump these two things and pick the
Actually, we need
permanent
to
register?
jump three things because there's the at the points that the E register points to, there's the continuation environment, which is the next, like it's the address of the next stack frame after this one is popped.
So like this.
Then we have, yeah, then we have two more cells for the program counter and for the size. And we should actually reach the size and do a bounce check on that to avoid overflowings.
That makes total sense. So you're telling me to do 2 here.
It should be E register plus 3 plus the index, but before we do that, we need to check that the index is actually inside of this frame. Like we need to check if the
If
index is less than the
plus 2, let's use what you like. Index of register is
less
uh,
than E register plus 2, but it needs to be a stack get of E register plus 2.
stack get of e register plus 2. So this is what? A cell in memory then. Store.
It's a cell in memory which contains the size of the stack frame.
Yeah, let's actually use that name. Stack frame size. Damn. Then we do this. These will return to us. Wait a moment. Okay, so I need to pass the store. There. What is the problem? Has type unit. No, this doesn't have type unit. Okay, it was just the if. Okay, this returns to us a cell, right, Marin?
Yes.
So a cell that has a particular type then.
Yeah,
Uh,
it should be. I think we're actually storing it as an address because that's what we use to use numbers, like to have
damn,
numbers in memory.
damn. Okay, we are already with two nested pattern matchings, so probably gonna have to use the let plus at some point.
Yeah, if it's an address, we grab the integer inside of the address and we use that to do the bounce checking. Like
Hmm. Then everything else,
explodes catastrophically.
yeah. Uh, this is
Invalid stack size.
yeah invalid stack size, not
Not a number.
address. Then when you're calling it bounce checking, but we're gonna compare the index of register to see if it's within the size.
It needs to be less than the size, yes.
Okay, so something like that. Which, by the way, I don't know. How do you do ifs in OCaml?
If, if
Yeah,
then else.
is
It
it like
should be.
this?
Yes.
Okay. So in the case of
Can I just can I just say it's kind of silly that Haskell has if then else syntax when if could just be a function.
but Haskell has multi ifs, so you can. It's way better than this thing. Multi-way ifs. That's the name of it.
Oh right, to avoid nesting on the final argument. I see.
Hmm.
You can type else if as well. You're back.
So in the case of else, that means that we have a fail.
Yeah, that would be
Stack
like a
over
stack of
underflow.
could be an overflow as well, actually. Um,
Yeah, no, actually, it needs to be an overflow because that means that the index of register is. It could be an underflow. You're right because this can be negative from principle. But in our case, I think it's going to be more descriptive to have this error as a stack overflow.
and it
Uh,
should be less than the size strictly because
yes, that's true. Okay, if that is the case, then we
then we
do
do the
this
thing.
thing
Yeah.
and damn. Look at this code, dude. Uh, there's probably a way better way to do this, but well, baby steps. Okay, so in the case that we know this, we're gonna actually use index of register here then.
E-register plus 3
3,
plus
this.
yeah,
That will give us, we are writing that structure
into the store.
into the store, and we are doing that. Man, I need to
So we
remember
can
the semantics of the permanent registers. Wait a moment. We are doing that because the register that needs to the register information out of which has the index that we want is on the stack.
yeah, exactly.
Damn.
Um, I mean, it's kind of silly that we call it a register when it's actually a slot on the stack, but that's the book. That's the book's name for it. So,
Okay. So in that case, we just do this.
yep.
What is it complaining about? This expression has type that, but an expression is expected to have that. I am
Oh, I think
confused.
we're missing an argument on the stack put, actually. Yeah, we're
Okay,
missing the previous store.
you are completely right. Okay, damn. Okay, so do you think this type of operation, we're gonna have to do these type of shifts for every single one of them?
Yeah, except some of them read the register and others write the register. So, you know.
Okay, but in that particular case, what you said, can we make this a function
Yeah,
that can be reused many times?
we probably should actually.
Okay, so what are we gonna call that auxiliary function up here?
We should make a pair of functions actually, one for reading and one for
Yeah,
writing, and then
yeah,
we can
but
just
baby
call them.
steps. Baby steps. Writing first. Which name?
Uh, Set register, I guess.
What does it receive? And what does it return?
Takes a register, a computer, and a cell. We can tweak the order to make it convenient.
I think the computer. Well, let's make the cell first. And then we can grab the computer.
And it's going to return another computer. Yeah.
So I also should pick this. Um, okay. So which things do we need for that? We need the E register, the X registers, and the store. We actually need those. Then we grab this thing. Actually grab this thing. We throw it in here. We throw it in there. Um,
We need to
uh,
tweak this a little bit because uh, in the original code, we're returning the registers and the store. We need to return
yeah,
an
no,
entire
no.
computer here.
Yeah, no, that's 100% makes total sense. Okay, here for instance, right? We're gonna have to do computa with X registers equal, uh, and the store is actually kept the same, so this can actually go away like this. And we also need the structure. So why was that the name that I gave?
Because before, this is a function that deals specifically with structures, but we actually need to put, it can be any cell,
Yeah, so I'm gonna
technically.
put cell here. Awesome. So in the other case, we do these things, more things, then here we do cell again, and then here we're gonna do computa with
With
store.
store. Yeah,
Okay, that's it for that one, which kind of
that, that,
means,
that's actually pretty okay.
yeah, that's pretty okay. Uh, there's a tiny problem. There's a tiny, actually no, I can just do let computa,
Yeah, light computer.
set register computer and structure, and then all of this can go away. And in this level, we don't need this anymore. What do you feel? Is that good enough?
I think it is.
Let's make the brother read. Actually, let's make it same amount of letters because I know you like that. What should be the arguments?
Um, Register and computer. We don't need the cell because we're getting the cell.
Are we gonna return the cell?
We're returning the cell, yes.
Makes total
But here's the
sense.
question, Lemus. Is it the perfect cell?
That was a good one. Okay, so when reading it, what is the first thing that we shall do? I guess do a match on the register again.
Yeah.
Okay, let's go with the temporary first. What should we do with the temporary?
We just need to get um, the value from the X registers component of the computer.
Oh, reading is way easier then.
It is.
Um, I need an
Or actually,
example.
dealing with the X registers is easier. With the Y register, we still need to do the same kind of bounce checking. But then we just need to do a get. We don't need to do a stack put, and we don't need to return an entire computer.
Y registers. And then you said this type. Okay, so in the case of a Y register, repeat please.
We do a bounce check, same as we did before.
Using the stack frame,
Yes.
but using the E registers too.
Yeah, using the E register too.
There. We get stuck from the stack. We check if it's an address. And then we do this check, right?
We do the check, and then instead of doing the let store and return the computer, we just do a stack get.
And the type of this is store and index of register. We actually don't need
No,
the
we
go
do
on.
need to do the E register plus 3 plus index.
Why?
Because otherwise we're just going to read from the wrong place, right? Because there's 3 values that belong to the stack frame but are not registers.
That's true.
Or rather, they are not Y registers. They contain the program counter and the pointer to the next stack frame
Dude,
in
we
the
don't
side.
use anything from the. No, we do use stuff from the computer. That was a lie. We don't use the Y registers, right?
We don't. Actually, I don't remember why we have that because they exist in the stack. So
I think it was just anxiety.
I see.
What is it complaining about though? Oh, I'm not using the computer, I guess. Yep. Let's actually remove this from the computer. Uh, okay, so we have these two auxiliary functions now. We have the set register and the get register. So now we need to go through all the functions. And everywhere we are doing a get using the index of a register, we need to stop doing that and call these ones.
Yeah, exactly.
Okay, so we did already with put structure. It just works. This one. This is doing an add. So I believe this is put register, set register, I guess.
It is.
So in that case, I'm just copying this thing. And instead of structure, it's reference. And I need to change the type of this to be cell register and change this to that. This is no longer necessary. Okay, you can stop him, Marin. I will go through here.
Don't stop me now.
This is doing a find, so this is a get register.
This is a get register, yes.
Uh, but what is this getting though? What is this? This is a cell. Okay, so this is gonna be just cell register. Instead of doing that, we're gonna do get register. You pass the register to it, and you pass the computer to it, and that's pretty much it. I just noticed we are not using this.
We
Right?
were, but we don't didn't need to for some reason.
Okay. Deref. This is a recursive function that keeps going on and on and on and on, right?
Yeah, no, this is for variables. It doesn't have anything to do with registers directly.
Yeah. Okay, so we have a bind here, which is just an auxiliary function. We have get structure, so I think this will be the one. So we do a deref, but we don't have an index of register anymore. So let's go with the types. Cell dot register. This, oh, we need to change the deref because the deref was receiving such a value.
Hmm.
Huh. Um, now what?
Hmm. Hmm.
I'm a little confused because to me it doesn't make sense for the
Yeah, no, I
index of
think
a
that.
register for the deref to be an Y register at all.
Yeah, I think the previous implementation was actually wrong because okay, here's the thing. The registers they can contain variables, right?
Yes.
And then the variables contain an address pointing to somewhere else or to the variable itself if it's unbound, right?
Yes.
And the deref is meant to like take a variable and either return the thing that it points to if it's bound or just return the variable if it's unbound.
Yes.
I guess in this case it returns the address of the variable, not the actual variable, but anyways. So yeah, it doesn't actually make sense for you to take an index of a register and pass it to deref. It should actually be, we need to get the value of the register, we need to check that it's a variable, we take the address in the variable and give it to deref, and that should work, I think.
But that is different than what the book said, though.
Is it?
Mm-hmm. The book doesn't do any of those extra checks that. I guess it makes sense what you said, but just a heads up. So var main, which is get register computer. Then we need to do a match on that. So I'm actually gonna do that directly. So that, and you said that it must be a variable, right?
Yes.
It must be a variable. We don't have variables on this level.
Don't we?
No, we have these.
Hmm. Huh. I guess it would be a reference, maybe. Maybe.
Okay, we're gonna YOLO it then. You only live once. Which, by the way, I don't know if you noticed. Look at what we're doing later. Does this ring a bell?
Uh, it's vaguely familiar.
Okay. So, uh, you're saying that if it's a reference, we're gonna put that value here.
Yeah.
Okay. What if it's not a reference?
Then this is wrong, I think. Because, like, get
Unreachable.
structure. The first thing that get structure does, get structure.
I have no recollection, by the way. I think getStructure was one of the first functions that we ever did.
Ah,
Yeah, it dereferences the value of the it dereferences the content of the register. Huh. Hmm. Oh, I think the registers are always supposed to contain references then, probably, maybe, potentially.
I don't know, actually. We didn't assume that before, though.
Because like if you go to the definition of get structure in the book, the first thing that it does is it dereferences the contents of the register, which is like deref takes an address. So this is assuming that the register contains an address.
I agree with that. That makes sense. Here, so we do
Yeah.
deref from the xi, which is an x register. So this is yeah, this is 100% assuming that. I agree with that. So are we gonna just roll with this and see what happens?
Yeah, sure. If it breaks, we can fix it later.
Well, we can, but I am a little bit concerned about this particular instance of this strategy because we have so many functions that we have absolutely no idea if they work as they were supposed to. And if one of them will be wrong, we're gonna have to add a bunch of prints everywhere to know exactly where the heck the problem started. And there will be another problem, which is that the functions afterwards, the wrong one, may also be wrong. So like it's gonna be a shit show.
Ah,
But let's go. Okay, so this is doing an
we
add of the index of register. This is already doing. It's supposed to be doing a set.
if we mess up lemons, we can just blame the beasts.
Sure, man, sure. Let computer.
That's a reference, by the way.
Yeah, no, I imagine that. Set register, register, computer in. There's something wrong. There's something called value. Probably I got the order wrong. Value there. Nope. And there we go. And we're gonna do a very similar thingy in here. But instead of value, it's reference. And there it is. Unify. This is the one with the while loop. This is the wild one. Yeah. And it uses two addresses, which I already forgot. Okay, are these addresses for real or are these addresses inside of a register?
They would be inside of a register because registers cannot contain integers directly.
So you're basically telling me that probably this type can go away entirely, right?
Uh, bind, if I'm not mistaken, bind is like
Is bind also supposed to be register stuff here?
bind is supposed to work with uh, cells, I think. Like, and one, at least one of them needs to be a variable, a reference.
Where is the definition of bind in the book?
I think it's way up.
Let's see
I'm,
the notation, because if there's a bunch of x's alongside the numbers, that means that we need to change bind as well. I don't remember what bind is supposed to do. That's why I'm asking. Are you sure? I'm still going.
uh,
I think I
maybe it
went to.
isn't up. Bind. Bind.
No, and it's not any of those. No.
Bind.
I think there isn't a function called bind. I think we created this name, maybe.
The name is used by the book, but actually I don't think there's a proper definition for it.
Where are we using it? We are using it
Uh,
inside get structure. So what is the get
Lemos,
structure? Go.
page 32 of the PDF,
32.
which is where you are. It's the bottom. It's the final paragraph on this page.
Oh, here it is. Bind address and H register to effectuate the binding of the heap cell rather than heap this, for reasons that will become clear later. The bind operation is performed on two store addresses. Okay, so this is not registers.
No, this is addresses, actual addresses, apparently.
Okay, so we actually don't need to go replacing everything then. Sometimes it will be address. We need to check it out individually then. Let's check unify. Where is unify? This one. Okay, it's saying here that A1 and A2 of unify are addresses. Okay? So
Okay.
are these really addresses or I think it must be because otherwise it would be that they're using the XI notation here, right?
Yeah, no, this is an operation that works on the heap, I think.
A PDL, apparently.
Yeah, that's a section of the heap.
Okay, so this one I'm gonna jump over. Then
Well,
we're
it's
gonna
not properly called the heap, right? Because the heap is the name of a particular section of the store. But yeah, it's in the store.
yeah. Okay, I'm gonna jump over that. There is a find here, so I think this is another place that we need to swap the type. So unify value, register there. Oof, 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 Marinho. Look at that. Look at line
Mm,
160 there.
160.
Unify expects two addresses, and we were using in the original thing the
Index
index of a
of
register as
register.
one of the addresses.
Yeah, no, we should grab the contents of the register and
Do a match on it, see if it's a reference,
or
right?
an address maybe. We will need to double check the cell types later, I probably.
Oh, I think there are addresses and references in here.
Yeah, and they actually are different things.
I don't recall which one is which.
An address is basically just a raw number. We usually use it as a pointer. A reference is actually a variable, like semantically a variable.
Okay, but in this case though, get structure. We are pattern matching on reference. This should be address then.
Should it? It probably should.
I don't think references make sense in this context because we are using the values from the registers as addresses.
Okay. Okay.
Uh, so here we're gonna have to do what you said. We're gonna have to do a match uh, of the. This is a get register, and if this is an address, then we're gonna do this shiz. Otherwise, this is an error, right?
Yeah.
Fail width. What's the error on this one? I'm gonna put unreachable for now. Unreachable unify value. There it is. And then finally, we have the same situation that we had before, which is swap. Yeah, swap this with a get register. Register computer, and we don't need this anymore. Okay, put variable. We receive two indexes of registers. Same with put value, by the way. So are we gonna swap those two indexes for registers?
Hmm. Put variable.
Yeah, this is a very recent instruction that we implemented. I think this came with L2.
Yeah, this takes two registers. This takes two registers.
Okay, so cell register, cell register. Oops. There we go. Then we need to do computer. Actually, it's a computer on a computer. Okay, I'm actually gonna swap this with a pipe. So the first thing that you need to do is to do this stuff with the thing. So set register, you pick the A register, you set the reference passing the computer, then you grab that, you set it again using the X this time, passing the reference again, and that's it. That should be enough. What are you expecting there? Register, cell, then a T, then returns a T. What's the problem? This expression has type this, but this is not a function. It cannot be applied. What? What the heck? What is
Hmm.
wrong here? Oh, in. Okay. Um, I think this is exactly the same, but reading. Boom, boom. So cell register on it. There we go. This is doing a find. So this is get register. Pass this in. I forgot. X. Then this is doing another thing. So computer. Actually, this can just be that. So this is going to be set register a register value computer. Okay, almost there. Um, Variable reading. So this is doing a find. So this is going to become a get register a register computer. Uh, what? Oh, this is correct. What's the problem? Oh, type. So register, and this turns into a that. So I'm gonna do this. Uh, do this type of shit, but this is X. Get value is just unify. Uh, the allocate doesn't use registers, so
Nope, it doesn't.
and allocate also doesn't. So is that it? Did we just fixed everything?
I think so. Maybe.
It sounds hard to believe, but
uh, okay, but in that case we don't need this anymore because we don't need to know which type of register it is. That's being handled individually. Is that it for get structure money?
I think so.
Damn. Okay, so let's proceed. So next instruction, put structure. And somebody needs to remind me when we get to these two, we need to do something special about it.
Yep.
Put structure has the same content of get structure, so I'm assuming this is also name everything in register and stuff.
Yes.
Okay, so what are the arguments for our put structure function? These. So let's see. Let's swap, not that. Put. This is expecting the register first, for whatever reason. Okay, consistency is a thing, but we can fix that later. Uh,
Amazing. I think we are following. Well, no, the instruction format is based on the book, but the functions are not.
put variable. Put variable. This thing takes two registers. I'm assuming this is actually grabbing one something called an X register and something called an A register. I don't recall which one is which.
Uh, it can actually take registers arbitrarily. Like an A register is really just an X register that has been used for an argument to a predicate.
Copy this. So there should be a put variable up there, and there is. I gotta say, although I think this approach gives incredible amounts of anxiety because you don't know if any of these things actually work, especially this one. The fact that now we have all the necessary preconditions to make a simple eval is kind of cool.
I mean, we could have written eval earlier. It's just that we didn't have a compiler to create the programs that we wanted to run, right? In eval.
Yeah, yeah, but that would be not very anticlimactic, I would say. Uh, so get variable, which also takes two things. So probably this. Uh, so there, and I'm gonna assume that I can just swap get here, and I can. Okay, set variable register. I have another question. This is a Prolog type language, right? So how are we supposed to get the available potential answers for our queries?
What do you mean?
Like we are making the evaluator, we are making something that picks a tape of of imaginary binary, let's say, and it's gonna do some operations on it. And when are we gonna spit the potential answers?
When are you going to spit the potential answers?
Well, at the end, presumably.
Yeah, but how are we gonna accumulate that, Marin? That's kind of my question. How that's gonna
I, s-
go?
I still don't follow the question.
I think he wants to know, like, what if a predicate has multiple answers?
Yeah,
Like,
Mm-hmm.
if it's non-deterministic.
yeah.
But the thing is, we don't have a language that lets us do that yet.
Oh, so L2 doesn't allow that to happen.
No, because we don't have choice. We don't have or yet. We just have and.
Yeah, we need disjunction to do non-determinism, right? So we need some kind of branching, actually. Disjunction is one way.
Okay, there we go. Set value. Done. Unify variable. Uh, Unify variable. Okay. Okay, so get value and put value. I'm gonna assume they are similar to these two.
Yeah, they kind of are. Kinda. Slightly. A little bit. Maybe.
Now, even Marin is non-deterministic.
Value there. Oh, this is okay. Get value is wrong. Oh, because this is just unify. Oof, 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 oof.
Huh.
Okay, so that means that we cannot just do what I just did because these things are registers, but get value because it's unify. In fact, it expects two addresses. In fact.
Yeah, it can't just be unify, I don't think. It needs to be.
I think I did that because the book also does.
Huh. That's a little weird.
Yeah, while you check that out, I will continue with the things here. Uh, so
Okay, the
unif
book actually does that. That is.
yeah, that would be a type of genius trick that I will never try myself.
I don't remember. Do the registers need to contain addresses? Because if so, that would actually explain a lot of things.
uh, well, let's assume that that might be the case. What then?
Uh, M0 is endowed with a sufficient number of registers to be used to store heap data temporarily as terms are being built. As thus, the contents of such a register will have the format of a heap cell. Yeah, no, it doesn't have to be an address necessarily.
Okay. Deallocate. Boom, 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 boom. Okay, so we need to fix that get value there, and we need to start working on the exceptions of the call and the proceed. So let's start with the get value one. If it's not unified, are we gonna have to do two get registers on it, pattern match on both to see if they are addresses, and then pipe that into the function?
Yeah, that would be the easier thing to do, I think.
Okay, not what I wanted. Let's do it then. I'm gonna change the names of these things. So this is gonna be match on two things: get register x register computer, get register a register computer with uh, if they are both address. If that's the case, then we do this thing.
Otherwise, we catastrophically explode.
Yeah. Fail with um unreachable get value. Okay, special cases now. The call and the proceed. Let's start with call. This one has a tag, which is basically a string, and it has a number. Is this the arity? Vaguely
Yeah,
remember.
it is the arity. It is the arity.
Okay, what do we do in that case?
This is something I've been thinking about. We don't actually have like a place um, to map functors to memory addresses, do we?
Functors to memory addresses. Do you mean like functor in this case would be the analogous of a function?
Well, yes, it would be just a tag and a narrative because the actual arguments would be in registers, right? But yeah, we don't actually have a mapping to say, okay, given a tag and a narrative, where is the code for this thing?
But I believe we already used call before when compiling.
We
Yeah, here
don't
it
need
is.
that for compiling, though.
We did.
No, we don't. Like, we don't need that mapping. We just need the name and the arity, but we don't actually need the. We don't need to know where in memory the code for that function lives. Well, that predicate, I should
But
say.
how are we gonna know that? That needs to be done on the compiler level, no?
Yes, we need to keep track of that when we emit the code and
Yeah, so
save
that's
that
definitely
information
not happening
somewhere.
today. But our program that I want to run will not use call anyway. So fail with,
Not implemented.
yeah, not yet implemented. Call is not yet implemented. What about proceed?
I think proceed is basically return, if I'm not mistaken.
But that
Um,
means that call, for that to make sense, call should make sense as well, I believe.
Actually, no, because for
Really?
proceed, we just need to pop the stack and copy the and restore the registers, the program counter, the we need to restore the program counter, we need to restore the E register, and we need to I think that's it actually.
Okay, let's actually make a function just for that then. Okay. So, as far as I understood from what you said, that this just picks a computer and returns a new one.
Yeah, it looks at the top stack frame, it grabs the two values that we keep skipping whenever we do a register lookup.
So that means the why we do plus two on that thing.
Yeah, we need to grab the value at E, which is the previous E that we're going to restore, and at E plus 1, which is the program counter that we're going to restore to return to.
We don't need CP register then, or P register in here.
No, no, because we're going to override them.
Yes.
Yes.
Okay, so let's start with what you said. You said to do a lookup. So I believe it will be something like store stack get, right?
Yeah, stack get, we
Pass the store, and the
use
address is the E register.
E register and E register plus 1. Yeah.
So what is the name of the E register not plus one? It is in the image on the book, but I don't remember.
The E register, if I'm not mistaken, is the previous E register.
Sure. Ooh. Uh, previous previous E, and the other one. What is the E register plus one?
That's the previous program counter.
Okay, so P register store stack get store E register plus one. Then I'm gonna do the trick that Marinho, well, Margueta taught us, which is to just use the same names there, there, and what else?
You just need to compose the record again, by the way, to use that.
No,
So it's
yes.
not just magical,
No,
like,
it is magical because you can just do this type of shit. That's what I meant.
yeah, yeah, but you need to do that. That's my point.
Yes, no, 100%. I'm just asking Marinho if there's anything else aside from popping these two.
No, it's just popping these two and returning the new computer.
P register and E register. What am I doing wrong?
Oh, right, and they need to be addresses, of course.
Oh, you mean like they need
Yeah,
to
we
be
need to
addressed. So
check that they are
cell
actually.
address.
No, no, we need to check that they are actually addresses, and then we just. Because the P register and E register in the computers are just
Oh,
integers, you see?
okay.
But when we save them in memory, we need to wrap them in addresses because memory contains cells.
There. So they need to both be addresses. E there, 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 And what's that again? Fail catastrophically, I guess.
Yeah, fail
Unreachable.
catastrophically.
Proceed. There's something. This expression has type string. Oh, I forgot the fail. Fail with. Okay, so this is our function. Oops. This is our function, so let's go down here. And what's going to happen is the following. Oh, but we don't change the P register here then. We need to pop the
Mm,
old one to continue the execution from after we return.
yes, which proceed already does, so we can just call the function.
Uh, damn. Is that it?
Uh, the only thing that concerns me a little bit is whether the allocate function is correct.
Okay, we can read it. This is the
Because
allocate
here,
function.
okay, allocate function
Oh, this
takes
comment needs to
account,
be here. I remember.
yeah, takes account of, oh, okay, we're doing p register plus 1 here. Um, and we're actually incrementing it already. So we don't need to do the p register plus 1 after the allocate because the instruction already does it.
Like this.
Like this.
Okay, let's see.
Uh, Actually, I'm not sure.
It compiles.
Looking at, yeah, because we're doing a deallocate before calling proceed, right?
Damn. We're calling what? Deallocate before proceed. I think yes, but the book says to do it so.
That means actually that the current implementation of proceed doesn't really work.
Wait, proceed is just grabbing CP and putting back to P. So maybe that's why we have CP register there.
Oh, I see.
Which,
And
by the
CP
way,
is
this is the
actually,
implementation of call.
well, for L2 actually.
Well, but that's what we have. We have L2, don't we?
Call p plus instruction size. So, oh no, but it's the second line. The second line actually is what we don't have.
You mean this? Oh, this. This is literally
Yeah,
dereferencing this.
yeah. We need to know. Okay, this predicate. Where is the code for it? We don't have that information yet.
Okay, so but this makes sense now. But for that to be the case, I think our proceed is now incorrect. Because the proceed
Well,
that we are supposed to use is to just grab the CP. That call will be responsible for writing it, and just put it back to P.
okay, yeah, that actually makes more sense because, like, if proceed actually read from the stack, you can't call the allocate before proceed because then you're going to lose the information that you wanted to use, right?
Okay, but now the question becomes, can we run a program without having call and proceed?
Uh,
I think,
in L2, no, actually.
yeah, but imagine that you only have facts and a single thing with a body that doesn't do another call or something like that. Can
I mean,
we?
we can try, but
No, but I don't want it to fail. I don't want it to
then
fail.
just then just don't write the failure. uh,
Okay. Actually, this is very easy to do. I'm actually gonna just fix this. So this is CP register, and all this can go away. And this is gonna be computer with P register equals CP register. Done. Uh, that's it. So we don't have call. We actually don't have call. So let me ask the simpler example. So Marinho, this program, we don't care about that. This doesn't help us in any regard, right? Do you agree?
I agree,
So we actually want to be able to run stuff like this, right?
but we
But
need call for that.
this will be a call.
Yes.
Damn. So that means that we cannot avoid it. We need to write the mapping between the functor, basically
Yeah.
dereferencing functors.
Yeah. Basically, we need to implement a symbol table, and we need to populate that symbol table during the compilation process.
We have half an hour. Let's try. Uh, so that means adding something to the compiler immediately, right?
Yeah.
So what are we gonna do here? Functor table? What do you say?
I guess that works.
So I think we need another map. Um, functor map. So this is a bat map. Make. Are we gonna do with stuff like this?
ast.funct, that's literally just a label and a narrative, right?
Yes.
A tag. Yeah, we can do that. It takes one of those and it needs to return.
But there's a problem. This takes a module.
This takes a module, and that's a type, right?
Yes. Well, how do you solve this shit, Magetta?
Oh, what?
How do you make a generic? Are you supposed to be able to make a map using the keys as a type instead of a module?
Wait, a map using the keys as a type? What?
No, the types as keys.
The types as
So
keys.
let me give you an example. So imagine that you have a func, which is this thing.
Just give me a sec.
We can just make a module that
Go on.
re-exports that func under the name t. That should work, no?
That's jank though.
Can you explain, Lemons? I believe I
Yes.
got it.
We have in this module called AST, we have a couple of types.
Uh-huh.
We want to make a map in which the key is our values of this type.
Oh, I see. I see.
So
Yes, if you
our problem is
got
these
it.
things get modules.
Mm-hmm. Yeah. So you need to do exactly as you're doing there. You're using batteries map, not the normal map, right?
Yeah.
Uh, remove the func,
Remove the
like
func,
AST func. So that should work. However, it will pick the T of the
which is
module.
not what we want.
So you need to make another module and put that inside.
Just
Oh,
do this, Lemos.
so make a
Yeah, you
file
can make
with
a.
just that.
I mean,
No,
you can
not a
make a.
file.
No,
You can
no,
just write that
here's
in line.
like go to the other file. Another option.
So go
Go
to
to the
the
other
which
file.
file? This one?
Which yes, this, and then you make another module. Call it whatever you want, like func, whatever.
Module func
Equals, yeah, and then struct, right? Don't forget.
struct.
And then this func will be, yeah, T done.
Um,
The problem is that it's recursive, so you
that
gotta
one.
fix.
Yeah, exactly. This is recursive with these other t here.
Lemos, you can just do this, no? Actually, this needs to be type.
Uh,
Well, Magetta knows. Magetta is the ML professional.
uh, let me see what Maria said here. Struct type at. You can make the module recursive also. You can make module rec that makes the whole module recursive. However, files are modules in OCaml, which is cringe. You shouldn't. But
Yeah.
you can make another module
Can't you
inside
just
of the
do this,
file.
Magetta? Like the second thing.
Yes, you can.
Okay, let's
Indeed,
see.
you can
That's
pass.
less jank than creating a file.
You can
Let me
pass
see.
the module as a value. Yes, I'll be right back.
That.
Oh, it's
Uh,
batmap.make, not just batmap, but yeah.
no. The value compare is required but not provided.
Oh, right. We need to compare.
So we
Can
need
we
to
do a
copy paste the, yes, that's exactly what I was about to say. We need to copy
deriving?
paste the deriving there. Holy Jesus, this is kind of like, I'm surprised this amount of jankiness came out of Marinho, but well. That's so freaking jank though. But okay.
Well, no, it's literally just an inline struct, an inline module instance.
Functor map. So this is gonna be what? What's the values? What are the values of this guy?
The value would be, I guess integers are sufficient because they would be memory addresses, right?
Yes. Okay. Functor map.
Back.
Okay. Here we are. Functor map empty.
Oh man, you could have just made an alias on the other file. That's another option as well.
The problem is that the other file already has a thing called T.
Yeah, but he could have made another module that has a T inside of the module that has an alias for the stfunc, right? Like you did.
Well, that is that. I think that's an option, Mageta, but I decided to go with the Marinho's jankiness.
Is it jankiness? Isn't this the whole point of ML?
Having modules as values, yes. I don't think that's
Isn't the whole point of ML?
being
Okay.
janky.
Yeah.
That's
Okay. Cool. So now the question becomes: this needs to be populated when we do a call. Am I right?
No, it needs to be populated when we emit code for a predicate, for a definition.
For a functor then.
No, no, for a definition.
Declaration.
Declaration, yes, that's the word we're using.
Okay. So when you said when you generate the code for it, right? So this function.
uh, yes, if we are generating code
For a
for a
declaration.
declaration,
So this one.
yeah, we need to add to the symbol table before we actually start emitting the code. We need to add the address of the the address that's going to be the next one that we're going to emit code, which I'm pretty sure that's just the length of the store. Well, no, actually, because that's pre-allocated. I think we have that information somewhere. I just don't remember where.
Wait, somewhere where? I'm gonna show you the compiler. So this is what we have
over the
inside.
rainbow.
Magenta, what? Sorry?
Over the rainbow.
For the
Somewhere
rainbow.
over the rainbow.
Yeah, that song.
You're welcome.
Thanks. Um, yeah, I think it's the P register. That's what we're calling it. I'm pretty sure.
Okay, so we need to go to the generate code. We are not using the P register, so we will. There. So, here, we're gonna do, what's it called? I keep forgetting the names of things. Uh, where is it? You need to do this type of stuff open, right? And I think you need
Lemons.
to do an add or something.
Forgetting the names of things is very bad. Don't do it.
Yeah, I agree with that.
I guess Alzheimer does eat all ages.
So we're gonna do add on that. So you need to create a func. So we're gonna do that right now. Then you need to pass the integer, which we know already it's the p register, and you need to pass the previous functor map, which means that we also need to destruct the functor map up here. So functor map
If you think about it, an ML
table of.
module is just a map, except it's typed.
Well, yes, table. So what do you have again on the func? We have the name f, the arity, and the elements. How are you gonna put the elements in there? Do we care about the
We
elements?
we don't care about the elements. We only care about the name and the arity.
So we need to change the map. This is not correct, in fact. Okay, if you're gonna embrace it,
We can just use a pair, no?
sure. Which is gonna be a string and an arity, right?
Right.
Uh, functor table. There it is. So here is going to be a tuple. Uh, what's going to be the name?
The tag of the head.
And the arity of the head, I imagine.
Yeah.
This is not that. This is name
I
f.
think it's name F, right? Yeah.
And then before we do this thing, we do compiler with functor
Functor table.
table. Is that it?
Should be. This won't work if we have multiple declarations for the same predicate.
No, but that's
But we
like
don't.
conflicting names, no?
No, that would be equivalent to like or, I guess.
Or. Oh,
Yeah,
you
it's
mean having multiple like this, I guess. No, not that. Multiple fathers, I guess.
yes.
This one would overwrite the previous one.
Yeah, this would have to be desugared into a disjunction before doing that, basically.
Ah, I see. Actually, I see. But that's what we're gonna do a second pass or something? How that's gonna work?
The easiest, the easiest way is probably just to do another pass.
Damn.
Uh,
Oh, we
but
can
we don't.
do we can do an AST expansion before, right? Just parse the
Oh,
AST, expand
pre-processing.
it. Yeah, well,
Okay.
just like Lisp, right? You expand the AST first, then give it back to be evaluated.
Actually, I don't know, Marinho and Mageto, you guys are more knowledgeable about, well, interpreters and compilers. What's best? You do a
No?
pre-processing with Mageta's strategy, or you do a post-processing with doing a second pass?
It needs to be post-processing in this case because the transformation is not local.
It's not
Oh.
local.
Yeah, because you can have multiple fathers like blah 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 blah
Oh
and then
yes,
father.
indeed. If it was, yes, that's right.
I see.
Well, you can make a global. I guess that's what you would call a pass. Yeah, never mind. That's just not just like a macro, right? You're not just expanding the AST. In that case,
No,
you're
yeah.
actually looking at the structure of the language of the program, rather, not just the language, and expanding
Yeah,
the structure, adapting to the program that you have at hand, not the.
yeah,
So it's closer to like what an optimizer does than instead of a macro expansion, right? Something like that.
yeah. This is like it's like there's some syntax sugar at the level of the AST essentially, and we need to get rid of that before we can properly emit the location of the predicate. Because if you just look at the surface syntax, you could have multiple definitions, but really they're just different parts of the same definition if you look at
Mhm.
the semantics of the language.
Yeah, agreed.
Agreed. What is wrong? Uh,
Ev- Everything.
Everything.
everything. I don't understand. Isn't it functor map the name of that?
Uh,
Yes,
it's
it is.
it's not. We need to put that in the computer probably.
No, we don't. Well, I decided to not to do that. I'm just passing the this thing as an argument to the eval.
Okay.
Yeah, but why is it complaining there? Syntax error after unclosed parens. Where is the freaking unclosed parens? Like what the? Oh, I know the problem. This will never work. This needs to be functor I call it map. No, I call it table. Unbound type. Type functor map. Yeah, but this is still a problem. Unbound type constructor. Why? Do I need? Do I don't need to export anything, right? This is just compiler dot something, right?
Uh, I think so.
So what's the heck's going on here? Why can't I just have this there? I don't follow.
That's a good question.
Unbound type constructor, unused variable. I
Unbound
get the
type
helps.
constructor, but this is a type. It's not a constructor.
Yeah, I'm confused. We also can just not trust LSP. I will not trust LSP. Uh, okay, but that means
How
Uh,
mistrustful.
what's the pain with LSP?
yeah. So we are on the evaluator module, and I want to import a
Mhm.
type that is present on the compiler one, and it's saying unbound type constructor there.
Unbound type constructor functor map. Isn't that a module?
No, that's this.
Also, it is instantiated. And that is from the compiler module.
Hmm.
Yes, that's. I think it's just tripping.
Yeah. Let's
If you do
implement
dune
call
build,
real quick.
if you do dune build and restart, it probably should work.
Yeah. So what we want to do here? I'm actually gonna put these side by side. So call receives a func, actually a pair, right, Marinho?
Yeah, it gets a tag and arity.
So a tag and arity, and what should return? A computer, and receives a computer and returns a new one.
It's also going to
There,
need the functor table.
that's also true. Functor table, compiler, functor map. Okay. So the first thing that we need to do, our instruction sizes are always one, right? Or am I
Yes.
mistaken? Okay.
Yes, every instruction occupies one cell, and that's the smallest addressable unit.
Okay, so this is actually p register, then say cp register equals p register plus 1, and I think this comment should be there. Um, then we do let p register equals, I need to do the open as well.
You need to do a get on the functor table.
Yeah, so functor map. Okay, let's go to the table there, here, copy this, um, put it in here, compiler. So functor table. I once again keep. Okay, so there's a find opt. I think we should do a find opt in this case because that's an important error to report, basically.
But if we call a function, a functor, a predicate that's not in the functor table, that's a bug in the compiler.
You're right. You're right, actually. So name arity, which kind of makes me. I think I'm gonna do ast tag this and just say functor. Ooh,
You can't use functor because it's a keyword.
I mean,
Haskell vibes.
you can if you put the thing, which you
Put the
did.
thing. What do you mean?
Uh,
The,
the the quote.
Oh,
at
prime
the end, yeah.
in, and then all of these can get away, and then we say computer with cp register, p register, and that's about it. Right, Marie?
Yes, and the call instruction when you go to eval, it shouldn't change the p register afterwards.
You should do what?
When you do the call instruction inside of eval, it should not
Oh,
change the
do the
p.
p register. Which, by the
Yeah,
way, I just noticed we need to do a recursion here, right?
do we?
Yeah, because we are basically saying do this, upgrade the register, and that's it. We're not calling eval again to continue the process.
We can make a loop around eval afterwards.
Okay. So this one will be call, uh, which reminds me, I need to get the tag, yeah, exactly this thing. So this is already a functor prime.
Well, it's more properly a predicate, no? A
Sure.
predicate name, I should say.
And oops, and the computer,
And we
and
need
I
to
did
pass
the
it the functor
functor
table.
table. Okay. Do you want to have like the function that we're gonna loop recurse is the one that we're gonna expose? I would like to expose eval instead of exposing loop. Marinho, what's your opinion?
Uh, I mean, we could expose both, because here's the thing. What if we just want to step through the execution, like
Awesome
one
idea.
instruction?
Hmm?
Yeah, eval step, and then eval is just eval step in a loop.
Uh, Copy
It
this.
just occurs to me, we don't have an instruction to finish the program, do we?
No, we don't.
Okay.
I think it would be fair to stop when you reach the first empty memory cell. What do you say?
That has the potential to go very wrong.
Well, but if the allocation and the compilation is correct, that will only happen after the program is done.
No, because you need to emit code for each you need to emit code for each predicate, right? And they are all going to live in the code area. Presumably you're going to start execution at address 0, right? But then after the initial predicate that begins at address 0, there will be the code of the other predicates.
Hmm. Okay, alright. I'm actually not sure. I'm actually not too sure. Uh, we don't need to we don't need to pass. Okay, this is a little. Okay, so what do you suggest? Because this is gonna be inconvenient. Uh, but I guess. Well, let me just make the loop for now. So we're gonna do eval functor table eval step functor table computer.
Okay, when do we terminate?
Very good question. I have no idea. Uh, Ideas?
Mm, what I did for elevator chime, well, we did it. I did a similar thing when I did. Well, we did for the original chime, I think. I did it for elevator chime. There's basically a freaking boolean in the computer that says whether we halted or not.
That was great. That was truly great.
But I've read a
Compiler.
guy today talking that saying that he saw people adding indexes on booleans in a database. And I was like, what was the person expecting to have, man? Like, you sure you index booleans and then you get like two indexes. Like, what?
Damn.
Why do you even have booleans in a database to begin
That's
with?
a good question also, but I'm not even going on that today. Like, what the
Oh,
heck?
but if you have a but having booleans on database is like having nulls, no?
Necessarily. I mean, you might say that there's probably a you might say that there is a motive for you to have them, like in a relational way. If it's something that you would just want there as information, but it's not really part of your Wordle discourse, right? Maybe you could get away with them, but like, why would you index booleans, man? Like, you just have two
No,
options. Like,
that's just trolling memes. I was
Maybe you
more.
want to act. Maybe you want to like be able to query all the false thingies and all the true thingies separately. But like,
But isn't that isomorphic to having a null in there?
no, because a null means I don't know, right? A boolean means it's yes or no. So at least it's just binary logic. It's
Well,
just boolean logic.
well, but you can also do a select with a where with the null, no?
But a null, what is a null?
No, I know that semantically they are not the same thing, but I'm trying. That's why I
Hey,
said
man, it will
isomorphic.
depend on how the person that encoded the business logic with a null to tell you, right?
Yes,
They might be that they're just putting null as a value, right? That could be.
yes.
you could have like you could use null as false if you have a unit value.
Yeah, something
But then
like
you
that.
ha- but then you have unit in your database. What are you doing?
I'm so
Yes. Yes.
confused. What the heck is this error?
Uh. Oh, I know.
Okay, go master.
Because when you do that, the so that is an alias, right? For the
No, that's not an
font.
alias.
Right.
We are creating
No.
a
Can you
module out of thin air, creating a
Mm,
type T inside, which is just a tuple.
can you
So
actually do a
can you remove the
deriving on a
show?
tuple?
You can. Actually, you can. The problem is
Okay.
that it's complaining that you're not using it,
But that doesn't
which
make
is a bit
sense.
that doesn't indeed. Can you put a? I'll show you how to do something kinda forbidden.
That like it
Uh,
just doesn't make sense.
go there to that part to the definition.
By the
Uh,
way, I've been reading a paper recently that I think you're going to find interesting, so I'm gonna post it.
okay.
Okay.
On the end, before the end, can you put open close squared brackets?
Oh, I know. I think I know what's coming.
Warning, right? You definitely saw it coming.
Okay, but I forgot the syntax.
It's with an at sign.
At.
Double at, right? It's the same as deriving. Yeah. And then you put in a string space, and then you put the minus the error there, 32.
It's even more jank now.
Yes. And it might not work.
No. This is not
It
Jank. This is
didn't change
OCaml.
anything.
Yeah, it didn't because it's not being used on the. It's not complaining the use of this on that type, on the declaration, right? It's complaining on the top level. So it should be on the module, maybe.
Unused value declaration.
Can you remove it from there?
Maybe if you remove the deriving show, because
Uh,
we only need the odds, right?
yes, I think so. But if we want to print, it will be hell. But remove the warning lemmas. The warning doesn't go there. It goes after the functor map. If you want to put that. No, no I mean, maybe it's there. I don't know how modules behave, but in an assignment, it goes after the name of the variable.
Okay, that's something.
It worked, so
Jank.
I don't know.
Okay, so line 25. Let's see.
And
What
I
are you
didn't mean
mad?
there, by the way. I meant elsewhere, but
What
okay.
are you? Oh, I didn't save it. Okay. Unused. Okay. I actually don't care. Okay, that's progress. Reachable. Uh, Okay, we know for a fact. Oh, it's because of the infinite loop. Okay, so Marinho, have you decided when are we gonna stop?
Can we just put a freaking boolean there?
But when are we gonna do the boolean true?
It would be false by default, and then it would become true. We would need a new instruction, a halt instruction, to set the boolean to stop the machine. But then we will actually need to choose when to emit that instruction, which is like mildly annoying.
Uh, so you want to have the boolean inside the computer, I guess, inside the machine.
Uh, yeah.
Okay.
What we can do is say, okay,
Can't we just put a number that goes up to 30 and stop? Isn't that just easier?
what? You want to count reductions? We can do that.
Well, you do 30 steps of evolve. After 30, you stop. Huh?
Well, we can make eval take a counter, and if the counter is less than 1, we stop. If it's greater than 1, we do an eval step and call eval with counter decremented.
So if it's this, then computer,
Well, it needs to be less than 1, actually.
else. Oh, actually that's not true. This, but counter -1.
Yeah,
Cool. So go. And the answer is this. Oh, this function application is partial. Okay,
right,
that's true.
because now you need to give it how many
Let's put
steps.
30 there. Nope, didn't fix. Okay, we fixed the recursion, but now something else is broken.
Try doing eval with 1 step.
No?
Still unreachable.
Let's see what the heck we are attempting. What the heck? Okay. So we are attempting the allocate. Agree?
Yeah.
Okay, so that means that theoretically we went here and we did allocate. In there, oh, there is an unreachable here that I should have added allocate. Yep. Okay, so we actually got this in there, which I think means that we probably made some confusion between addresses and references, maybe.
Mm,
We can actually check that out.
allocate.
Allocate. Here it is. So we add the allocate. Now that's gonna take a while. So let's see if the evaluator is wrong first. Let's go.
Oh, we're allocating Y register, but that's the number of whatever.
Wait, which part is whatever?
Yeah, go back to the other file real quick. Uh, allocate head, we take the Y register from the compiler. Right, we're counting how many. Okay. Yeah, no, that's a number.
Yeah, Y register is a number. No, but the problem that we're having is that I think we're having a segmentation fault, basically. This is going outside of whatever it's supposed to go. It's going to the wrong cell.
Right, because we don't have a stack frame allocated at the beginning of the program.
Mm, good call. So how should we do that?
We could pre-allocate one, like with no arguments, but that feels wrong somehow.
That answer was great. That feels wrong somehow. Um, Okay, what are the other alternatives?
What are the other alternatives? What are the other alternatives?
I don't think we have
Allocate
another one,
takes an n.
which is the number of permanent variables, right?
Huh. I guess we would have to fill in a dummy. Ah, that feels so wrong though.
I mean, I understand why it feels wrong, but I don't have any other ideas personally.
Let's just yeah, let's just do it. It's not gonna stay like that, but yeah, just
We're gonna do it in here though. So,
y- yeah.
raw.
Just before we start the program.
Oh, I think my internet went to crap. Okay, am I back?
Yes.
Okay. Repeat, please.
Yeah, before we start the execution, we just set the low the we just set the lowest, like the stack address 0 to the stack base, I guess.
Wait, repeat. I'm gonna
Right, we
change
just
what to
need
what?
yeah, we need before we start execution, we need to do a stack put, a series of stack puts to set the like to manually set the stack frame. So
Oh damn. Okay, so before. Wait, you said before. Okay, so this is
before starting execution, before calling eval,
yes. Let's store. Tell me more.
right, we need to do a stack put. Um, we need to put the address of the stack of the base of the stack at the address 0 on the stack. So like the lowest.
I forgot already what is the. Okay, so what are we gonna put in there? In the zero.
We need to put the address of that same cell in memory. So I think that's the stack base, if I'm not mistaken.
Stack base.
Yeah, we have that number saved somewhere. I think it's also just the. I don't know if we're exporting it though.
I don't recall which number you're talking about.
Like, you know the address of the beginning of the stack?
Stack start.
Stack start, yeah, that's the name. And
This.
that's what we have to put in the first in stack 0, basically.
We're gonna put an address there with that number in there.
Yes.
Lib cell address store stack start, and I need to expose this now, which is kind of not ideal, but we can fix that later. Vol, and this is just an int. So there it is. I don't know if that's actually that's going to work, to be honest, but let's see.
Yeah, and then we actually need to fill in a couple more things. The stack address 1,
Wait a moment. Tell me more.
yeah, stack address 1 needs to be it needs to be an address of an instruction that will stop the machine execution, the program execution in the machine.
Wait,
Uh,
at which? Repeat it from the second part.
right, it needs to be the address of an instruction that will stop execution, basically.
The address of an instruction that. Okay, so you're talking about the address of a halt.
Yeah,
But where is the address of halt? We don't know that.
well, we can do a trick. We can just
Put
emit a
31 in
halt.
there.
What?
Do a 31. No, don't forget about it. Go on.
No, we can emit a halt after we finish emitting code for everything, and just remember that address, like at the end of the compilation.
I have a question. In the compiler, we have something called the P register. Is that the program counter of the compiler?
That's the program counter of the compiler, yes.
That means that we can use this to know the halt.
Yeah,
Interesting. Okay. So, damn, this is jank. Very jank.
it is.
Uh, let me think. Let me think. So I think the order doesn't matter, but I'm gonna put it before doing this thing. So we're gonna do lib store. Uh,
Uh,
we want a
no, no, no,
generic
no, no.
put here,
No, we need to do that after we finish compiling everything, Lemos.
which is we did. This is done compiling. Agree?
Let's see, part content with if it's empty, initial computer, and then we compile declarations and queries. We print some stuff, and then yeah, no, I think that's actually right.
Okay. So we want to go and do a put. Do we have access to generic put in here? I don't think we. No, we don't. But that's a code put because we're gonna put an instruction there, right?
Yeah, it is.
Okay, so that's actually okay. I'm starting to understand. So we're gonna do a code put in there, in which we're gonna put the instructions. So it's lib cell, and we're gonna introduce halt in there, and we're gonna do this given the compiler p register plus one, and we need the store
I
there.
think it's just p register actually.
Why?
I think that actually points to the next instruction, not the
Oh, okay.
not the last one.
Okay, so this is put in the halt there. This is put in the beginning of the stack frame, right?
Right.
What else are we missing?
Well, we need to put the address of the halt in the stack after the, like at position 1.
Okay, at position 1 you said.
Yeah, you just put the pointer to the stack
Compiler,
frame.
compiler p register, which is where the halt is, and we put that at 1 you said.
Compiler.pregister. It needs to be an address, not just a
No, that's
number.
true. I forgot about that. Lib cell address there. Is that more like it?
That's more like it. And then finally, we need to put a 0 at the third position at address 2 in the stack.
And that the reason for that is?
Because that says, okay, this frame has no permanent registers.
That makes sense. Uh, this is also incorrect. By the way, we already have this. It's called initial computer. Okay.
I think LSP is saying there's something broken with the
Yeah,
store.
but I don't really trust LSP.
Okay.
Let's go.
And you need to implement halt.
Oh, yes, that's true. But it's complaining that vol stack start is being not used, unused value, which is weird, but okay. We need to let's implement the thingy. So here we're gonna introduce halt, which means that we do not
We
need
do
the counter anymore.
What do you mean?
We don't need to have a counter. We can just go until we halt.
That's an option, yes.
Um, Um, okay, just for the sake of the meme, I'm gonna introduce a boolean just for that.
You don't need one though. You can just say that um, you just make the halt return the same computer and not do anything else.
Yeah,
And
but we
then
need
if
to
you
inform the non-step function to stop.
yes, if you get the same computer twice in a row, that means you halted.
You rather compare the computers, given that they are gigantic?
Well,
Damn, you prefer that than a boolean? That's hatred right there.
That's hatred.
Damn. Uh,
uh, I guess what we could do is, but then we would lose the eval step, which is kind of not nice.
yeah. I think I thought about doing the same thing that you thought, but it's inconvenient. I think I'm gonna do the boolean, and I don't care.
Okay.
Uh, does this work in OCaml by any chance? Can I just do that? Yes. Okay. I don't need the parentheses. Screw Lisp. There. There.
You
That's
should have said
harsh.
that with Marinho on the call.
Of course. Uh, that. 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 Halt.
Computer true.
Uh, I think it's a LSP just being broken. So just to make sure,
Halt.
I'm gonna solve
Halt is the only truth.
that, that. So then here we do let computer stop. Grab this, throw it in there. Uh, do this.
If stop, you
If
return the computer.
stop, uh, stop computer, then computer. Else
Eval computer.
evolve functor table uh, computer. Let's go. Okay, now we go back to the other problem. So how do you fix this one? I'm a little confused what it means to say not nobody's using that. How do you know? Exactly. Did I save this? Yes. Ideas, people.
Uh,
Like what the heck is going on here? Like this, literally, it is using it. What do you mean?
Store.stack start. But that's grabbing the stack start from the instance, right?
Yeah.
Hmm, which should be correct, I think. But it
Actually, let's actually
isn't.
ask Magetta. Actually, I think maybe this is where we're doing it wrong. Magetta,
What's that?
we have a vol, which is just a number inside a module, like here.
Okay. It's a value. So okay,
Exactly.
it's a variable.
Then we have an instance of this store module. We have something called the store, which is here. You see
Uh-huh.
there?
Yeah.
Yeah.
Oh, but it isn't actually. That's a finger tree of cells.
Oh, okay. So that's the problem. We need to. This actually needs to be a module, like this, right? Is that what I'm understanding here?
This needs to be.
Does a
This needs
machine
to
has a
be.
store? I think so, right? Yeah,
It should have,
we
yeah.
should do machine dot store dot the thing.
Yes.
Okay, so initial computer dot store dot stack start. Okay, that was the problem. No, it was not. I'm confused.
It's not initial computers. Initial computer is of type T from that module, but it's not
No, but the type
like
T has a store inside it. Agree?
type T.
Here it is.
Okay, there is a store.
Yep, there is a store
Uh,
there. No, man, but look, we are using it in here. Isn't that how you're supposed to do that? I think it is. I think we're just trolling.
oh, okay. This is from the instance of store inside of machine, and not from the
Yeah.
store.
So it's lib
Um,
machine store stack start. Nope. What the heck? What is going on?
I don't think. Go back to the module definition.
Which one? Machine or store?
Machine.
Mm-hmm.
Okay, we have store inside of machine, and it has the stack start, right?
Yeah. Yes, actually. We can just use the E register.
I guess.
That's really jank, but well. Boom, boom, boom. So initial computer E register, and then inside the store we actually remove this guy from there, and let's see how that goes. Okay, so unbound value lib.store.stack put. What do you mean? Oh, it's because it's the wrong store. I see the problem. We need to do the thing. And actually need to do that with multiple ones. So I'm actually gonna do it in a single. Oh, oops. Boom, 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 boom. There, machine dot. Okay, now it's gonna have a type error there. So this thing expects an A, then the store, then the store, and it returns a different. No, it was correct then. What am I missing here? You grab the A, you grab the int, which is this guy, then you grab the store, right?
Hmm.
So what is the problem? What is the problem? This one is easy.
Lib.
This expression has type lib.machine.cell.t, but an expression of type this was expected. Cell.instruction.
Oh, oh, it needs to be lib.machine.cell.instruction, and you need to pass lib.machine.instruction.halt as a parameter, or something like that. I don't remember the details.
Yeah, we should definitely do a let open here. Machine store. In again lib
Or we,
machine cell,
I mean, we can always blame the beasts.
of course. Then we do these things. Then we do these things. And what did you say? You said instruction.
It
This
needs to be a cell containing an instruction.
cell dot what?
Cell dot instruction, I think.
Unbound
Although,
module.
yeah, no, I think that's just the instruction now, no, because we did a let open.
Let's actually put. I think it's gonna get more readable if we add at least these modules back. So store. Oops. Store. Um, these ones are cell. Apparently it is not.
It should be cell dot instruction, and then I think it's instruction dot halt or something.
I don't know. What about this? Nope.
No, that doesn't work.
How did we do this before in the compiler? Add instruction. Oops. Oops. Cell dot instruction. Uh, yeah, let's see examples of add instruction. There it is. So it's just cell dot halt, I think. Marine. I think. I actually not sure. Did you mean PP instruction? No.
Shouldn't that instruction be uppercase?
Like this? Oh, okay, that was it. Damn. Wait, now we may be out of hardware.
What do
Uh,
you mean?
exactly what I said. We may have to bump it up. Is this enough?
It should be.
Okay, so we have a bug that we don't know where it is.
What's the bug?
Here,
Killing our
someone
floor
is trying
reach.
to do basically segmentation fault. That's what this is, right?
Basically.
No, but this is where we did a lot of progress anyway. So I'm gonna
Isn't
format it.
that... isn't that... Oh, I think I know the problem actually. Stack put and stack get, they don't take addresses relative to the start of the stack. They take absolute addresses, no?
No. Well, we can check, but maybe I'm wrong. Maybe that's the problem. Stack get. Okay. Uh. Oh, you mean when you say relative, do you mean like 10 plus the stack start?
Limited get, stack start, and then those are the bounds.
Yeah, but we don't do an addition. That's what I mean. So for instance,
Yeah,
the floor is the stack start, and this is gonna be the whatever. We don't do an operation here. You need to do
yeah,
to know the absolute. The
yeah.
absolutes.
We need to know. Yeah, because stack put and stack get, they do bounds checking, but they actually don't do relative addressing. Still absolute.
Yeah, but where are we using that assumption?
When we set up the first stack frame,
Here.
before we even eval the program. Yeah, there. See, we need to
Oh,
do
what
instead of...
I see what you're saying. We need to do e registers and e register plus one and e register plus two.
Yeah,
Okay, that I see. So let stack start. I'm gonna say that this is this thing. There we go. There. Then stack start. Stack start. Stack start plus. And finally stack start plus. This expression has type int. This is not a function. What? Oh, forgot the plus. Of course.
exception, exception not found.
Okay, so
That's
there,
very
there,
helpful.
no, there is a find somewhere in the middle of somewhere. Actually, we know that this is not in the compiler, so actually we can even detect how many finds we have. There are only two finds. This one in the get register and this one.
Hmm.
Okay, so let's start with this one. Can this be wrong? This is the call one. We just implemented this.
Find functor table.
If the functor table may be messed up, right?
It may be, yes.
Yeah, okay, but let's see the other find here. This one. What do you think about this one? This also throws an exception, by the way.
Get register.
Well, we can actually accelerate this discovery process. We can just put this fail before the match and say got here. I don't know if the compiler will allow me to do that. It did, and this is definitely not the place. Oh, I didn't save. Oh fuck. Okay, what's it complaining? Give me the print. Where is the print? Print. There we go. And we can just put something along the lines of got here. And then we just do that. And okay. That doesn't answer.
We should put another print immediately before the other find as well.
Sure.
This way we can identify which one exploded.
I think. Uh, Let me do a let x equals this. Print again x. There it is. So it is this one that failed.
But we have two got here's that are the same, no?
No. We got one got here, then the got here 2 didn't appear, which means that
No,
this
no, no, no,
failed.
no, no, but no, but there's another got here somewhere else, no? Oh
No,
wait,
no, there isn't.
okay.
So that means that our get register function is not working, surprisingly.
That,
This is the
that's
get
very.
register.
Hmm.
Okay, so we have an index of something that is not available on the X register. So what does this mean exactly?
It means we're trying to read from a register that's not being initialized, I guess.
Uh, well, I think we can finish here today. What do you think?
Sure, we made good progress, I think.
Yeah, no, we did. We basically plugged the evaluator into the compiler. Or rather, the other way around. The compiler's output is now being piped to the evaluator. We fixed the register problem. Well, we think we fixed. There's a problem somewhere, but this is hard to detect, right? We don't know if this is the problem in the compiler or in the evaluator at this point. We don't know that.
Uh, yeah.
So,
It could also be a problem in the program. There's that option as well.
which program are we running? We are running L2. We are running this program. Should that fail?
I
Actually,
mean,
yes. There is no definition of Q.
that is correct, actually.
Damn, I am understanding something. God damn. Okay, what about... okay, can we make a program that makes a valid output somehow? What do you say, Marin?
Uh, I mean,
Tough, huh?
given the semantics that we have available right now, yeah, it is tough actually.
Isn't it just a matter of adding two facts related to Q and R, and instead of using variables in them in the body, we just use hard-coded stuff?
We can
That
just have an we can just yeah we can just make facts with like variables saying, okay, Q holds for whatever and R holds for whatever.
like this, you mean?
Yeah, but the way this is written, we're actually going to try to call Q. We should put the definition for P first, I think.
Oh, the order matters. Is that the same in Prolog?
It isn't, but that's because we haven't like we're always executing from address 0, you see? We don't have
Mm,
the ability to set the entry point. That's the problem.
I see. Okay, but as far as I can understand, also correct me if I'm wrong. I can also change the name of these things.
Yeah, you can put whatever variables you want.
So this program should be runnable by our current implementation. Oops.
Probably.
My Emacs got crazy. What the heck happened? Running
Something.
Elm outside of context. Maget, are you there?
I am just switched to my iPad. Why?
My Emacs got insane.
Uh,
It's saying running Elm outside of context, but I didn't do anything.
press Ctrl G,
Doesn't work.
Ctrl X, left.
Okay, that did
Oh, I
work.
know. Keep pressing Ctrl X, X, L, left.
Uh, there, we can go into a buffer that I will show confidential stuff.
Uh, Ctrl X, right.
Yeah.
Press.
Okay, that
Yes,
that
there you
was
go.
okay. Magenta the savior. Do you think this should work, Marin?
Maybe.
Maybe. We're going with a maybe
There's
today.
yeah, it's a maybe.
Uh, okay, so we had an well, but I removed, right? I removed the stuff actually. Hmm. Why does the order matter though? I'm a little puzzled by
Because
that.
we're always executing from address 0.
But shouldn't these things be first because they are facts?
No, they will be later because we see them later in the code. We are not doing any reordering, Lemos.
Okay. Okay,
We
my question.
should eventually, but we aren't just yet.
Yeah, but now we still got an exception not found, right? And I would bet that this is happening is still on the get variable, on the get register, sorry, this thing, right?
Right.
Uh, Final check before we finish this. I'm just gonna pick this, put that in the evaluator and run it in here. Uh, Something. There we go. Yep. So it's still not finding it, actually.
Okay, we'll have to look into that then.
But damn, today was productive. We did a bunch of stuff.
And we reflected on ourselves.
Reflecting on ourselves. Uh, I'm gonna actually queue this one. Okay, so what happened? Okay. Update L2 example. Uh, Damn. Okay, here we're gonna say save functor address information for evaluation. Uh, introduce halt instruction. And finally, plug compiler into Evaluator. Oops. Woo! I'm gonna finish the recording now.